Hello guys, once again welcome to our YouTube channel Edu Hub, and as you know this part 5 of data analysis, so please be focused and without wasting time let's get started. Data analysis part 5.
Welcome back. So in the business intelligence realm, it's hard to find data that doesn't have some kind of date component. If you recall, our data model does have a so-called calendar or date table that has one row per date and spans our time frame of interest. But thus far, we haven't done very much interesting with this table, other than relating it to the data tables in our model. But that's about to change, thanks to DAX's time intelligence functions. These time intelligence functions in DAX allow us to perform date-driven analysis. Things like year-to-date sales, or month-over-month comparisons, or 30-day moving averages, just for example, far more easily than you could otherwise. So as you can see here in our finished example file, we're going to tackle displaying year-to-date revenue totals alongside the individual monthly totals. So if you look at the line in our pivot table for December 2018, for example, you'll see that in our revenue column, we have just the revenue for that particular month. But in our revenue year-to-date column, we have the revenue effectively for the entire year, or at least the part of the year we have data for from July to December, because that's the revenue year-to-date for December. Now, while DAX's time intelligence functions are going to make creating this metric pretty straightforward, we have a little bit of setup to do before we start using time intelligence functions. So let's dive into that. So while we have our dates table created, it's important to emphasize the central role that the dates table plays when it comes to time intelligence functions. Having a table like this, which has one row per date and whose date range spans the date ranges of all the data tables in our model, is absolutely essential. We basically can't use time intelligence functions without a date table like this in our data model. Now furthermore, this date table has to be related to the data tables in our model. And if you recall, and we'll confirm this by going to our diagram view, our dates table is in fact related to both our service calls table and our orders table on date. But there's one additional step we need to take before this dates table can be used as the official dates table for our data model. And that is to designate it as the date table for our data model. So if we go to the Design tab of this window, you'll see there's actually a button that allows us to mark this table as a date table. That lets the data model know this is our date table, which will be used as the basis for all these time intelligence functions we're about to explore. And while I could go ahead and do that, another option that we're given is to create our own date table from scratch right here in the data model. So if I click that button, you'll see we have the option to create a new date table. So let's see what happens if I do that. So after waiting a moment for Excel to finish its work, you'll see that we have a brand new calendar table, structured very similarly to our previous one with one row per date, and with a number of derived columns that Excel was kind enough to tack on by default, including some of the same ones that we derived ourselves when we were creating our previous dates table. Now while, as you can see, Excel gives us a lot of stuff here right out of the box, from the general structure of the table to these various derived columns, there are also a number of ways we can configure this table to meet our own needs. For example, if I click this date table button again, and then choose Update Range, you'll see that I have the option to change the range of dates encompassed by the table. But Excel was actually clever enough to look at our data and correctly guess an appropriate date range for this table. But if for whatever reason you ever wanted to extend, for example, the end date of the date range, it would be as simple as using this calendar picker in the date table range dialog box. We can also add derived columns to this table, just like we did our previous dates table. And if we go back to our previous dates table, you'll see that we have a couple of derived columns that were not automatically generated by the data model. So let's go ahead and port these formulas that generate these columns over to our new calendar table. So first I'll copy over our weekend column. So I'll copy that formula, go over to our calendar table, and then calling this column weekend. The only change I'll have to make is updating the reference in our if statement from pointing to the day name column in our dates table to the day of week column in our calendar table. And now I should be good to hit enter. And then for our quarter column, I'm actually going to show you a different way to derive quarter using a DAX function called format. So the format function takes in a value as its first argument, which in this case will be a date, and then for its second argument, it takes in a format pattern, which tells the format function how we want to format that value we fed it in the first argument. So if I want to create a column called quarter, I'll click under our add column heading, type quarter, equals, and then format. And then the value we want to format is the date column in this table. And now for the second argument, we'll tell the format function how we want this date to be formatted. Now we want it to be formatted as a quarter, so we'll just type in double quotes the letter Q for quarter. And then hit enter to lock it in. And as you can see, our formula is returning the number of the quarter corresponding with the date in each given row. Now because the format function returns a text string, we can actually concatenate a capital Q in front of this number to make for a nice viewer-friendly quarter value. So before our format function, I'll type a capital Q in quotes, and then glue that to the output of our format function with an ampersand, and then hit enter to lock it in. Awesome. At this point, we have successfully replicated our previous dates table with just a few clicks. So now the last step is to retire our dates table and then replace any references to it with our new calendar table. So I'll go back to our dates table and right-click and try to delete it. But now Excel is telling us this table was created by a query, so in order to change it, we need to change the query instead. And that's because we originally created this table based on an import we did through Power Query. So we'll have to go to Power Query to get rid of the table. So closing out of our data model, we'll go to the Data tab on the ribbon, then Get Data, launch Power Query Editor, and now we'll simply right-click our dates table and delete it, and then close out of Power Query. And now we'll go back to our data model. And now our first step is going to be to tie our new calendar table to our two data tables in the same way that our dates table was formerly. So we'll go to our diagram view and then zoom out just a bit. And now you'll see our calendar table kind of isolated over here to the right because we haven't yet defined any relationships to it. So we'll drag it back to roughly where our dates table was, and now just create relationships between that table and the order date field of our orders table, and also the call date field of our service calls table. All right, so now that our calendar table is fully integrated into the data model, let's go back to data view and see if we have any errors for any of our measures. Well, if we look at our service calls table, we'll see a little warning sign. So let's click that tab, and then scrolling up through all of our measures, we'll see that 2 display that warning, and if we hover over them, show us an error. But looking at the formula for the measure, it's pretty clear what's going on here. This measure is referencing the quarter name field from our dates table, So all we have to do is replace that reference with the quarter field from our new calendar table. And then hitting enter. And it looks like all of our errors have disappeared. So our calendar table at this point has fully replaced our former dates table. And because we created that table as a date table in the data model, our data model is aware of that table as our designated calendar table, which can be used to power our time intelligence functions. So at this point, at long last, we're ready to dive in and get our feet wet with time intelligence functions. So for our first step, let's create a simple pivot with year and month on rows and revenue on values. So I'll go to Insert, Pivot Table, from our data model, and then I'll drag in the year and month fields from our calendar table. And if you recall previously, when we dragged month name into a pivot table, the months were sorted alphabetically and not chronologically. But because our calendar table is now a designated date table, Excel recognizes those date names as things which should have a natural chronological sort order and sorts them that way instead of trying to sort them alphabetically. Just another perk of having a designated date table as opposed to just a table with dates that we use that way but isn't designated as such. So now I'll drag in our revenue measure. And now our goal will be to create a revenue year-to-date measure, which next to each month will show the total of the revenue for that year that that month belongs to up to that month. So for July of 2018, we should see the same total as July since that's the first month we have data for in 2018. But for December of 2018, we should see the year-to-date total for that year since that's the last month of the year. So to accomplish this, we're going to use a function called dates year-to-date, which is actually a member of a family of time intelligence functions, which all do something quite similar. There's also a dates month-to-date function and a dates quarter-to-date function, for example. So typically, you're not going to use dates year-to-date or any of its sibling functions on their own. Instead, you'll use them in the context of a calculate function to manipulate the filter context in that calculate function, kind of similar to how we saw the all function work previously. So here's how dates year-to-date manipulates filter context in calculate. It basically identifies the latest date in the current filter context. So for December 2018, that would be December 31st, 2018. It then expands the filter context backward to the beginning of the year that belongs to that particular date. So for the row of our pivot table corresponding to December 2018, our dates year-to-date function will yield a filter context that ranges from December 31st, 2018 all the way back to the very beginning of 2018. Now we only have data starting in July, so effectively it will allow us to sum those totals starting from whenever we had data in 2018 all the way to December 31st. Likewise, to look at another month, for example, say April of 2019, the dates year-to-date function is going to give us a filter context ranging from April 30th, 2019 all the way back to January 1st of 2019. So now that we know basically how dates year-to-date works, let's see it in action. So first I'll go to my Power Pivot tab and then create a new measure. And I'll assign it to my order details table and I'll call it revenue year-to-date. Now for my formula, I'll start with a calculate function. And then the measure or expression that we're calculating is just going to be revenue, because what we're really doing here is taking that revenue calculation and just applying a different filter to it so that we see year-to-date revenue in our pivot table instead of just revenue for a particular month. And now for our filter, that's where our dates year-to-date function comes in. So we'll type that out. And now you can see that we have one mandatory argument and one optional argument. We won't worry about the second argument for now. Most of the time, you're good to just enter the very first argument, which is dates. So with dates year to date, as with the vast majority of other time intelligence functions, the first argument is going to be the column from our date table or calendar table that has the actual date values. Remember when I said that our date table is absolutely crucial for our time intelligence functions to work properly? Well, this is an example of how. They need that column of dates in our date table to work. So we'll enter that column. And again, that's the only mandatory argument for the dates year to date function, so we'll close our parenthesis for that one, and then our second parenthesis for our calculate, and then we'll format our measure as currency, and then click OK. And looking at our resulting values, it seems like our measure is working as it should. But let's just test a few months to make sure. So rolling forward to 2020, for January, our revenue value and our revenue year-to-date values are the same, as you would expect. But if we go forward to, say, August, we see that our monthly value, our value for that 1 month in 2020, is $599,000. But if we sum up the values ranging from January 2020 all the way through August 2020, and then look down at the automatically generated totals in our status bar, it looks like they match. The sum of all of the individual monthly totals in 2020 through August is around 2.8 million, and that's also the number we get for August in our revenue year-to-date measure. Now there is one issue here that I have not pointed out yet that you won't see until you scroll to the bottom of the pivot table. And that's that once we get past the last month in the last year for which we have data, our revenue year-to-date measure keeps populating, even for months where we have no data. That's because, for these months, the concept of year-to-date revenue is technically still valid. You could accurately say that as of November, the year-to-date revenue total is 4.6 million, just as it was in August, the last month we have data. But while this is technically accurate, it's not really a great user experience and would probably be confusing to most end users. So what we need here is a way to conditionally make the output of our measure blank if the underlying revenue measure is blank. Now there's a fairly straightforward way to solve this problem, but this video has already gone a little bit long, so we'll tackle that in the next one. I'll see you then. Hey, welcome back. So when we left off, we had just managed to put a year-to-date revenue measure alongside a monthly breakout of revenue in our Power Pivot table. But there was one problem. Our measure is causing rows to be added to our pivot table for months that we don't even have data for, because it's still valid to say that there is a year-to-date total for those months. So how do we get rid of this dead weight from our pivot table? Well, the first step is to think about why, specifically, we don't want these rows in our pivot table. And that's because we don't have any actual revenue for those months. So what we need then is some way to get our newest measure, our revenue year-to-date measure, to return a blank if the revenue measure is blank. If you think that sounds like conditional logic, you'd be correct. But we need our logical condition to test whether the revenue measure is blank for a given set of coordinates in our pivot. That is to say, for a given year and month in this case. And that's where DAX's isBlank function comes in. IsBlank returns true at a certain set of coordinates in a pivot, that is to say, a specific intersection of row headers, column headers, and filters, if the measure or calculation we provide it is blank for those coordinates. So now we can use this function to test whether our revenue measure is returning blank, and if so, make our year-to-date revenue measure return blank as well. So now that we know about the isBlank function, let's use it to refactor our year-to-date revenue measure so that we only see it for months where we had actual revenue. So our first step, of course, will be to click our Power Pivot tab and then go into our measures and then choose Manage Measures because we're actually going to be editing an existing measure. And now looking down the list, I see our revenue year-to-date measure, so I'll click that to select it and then click Edit. And now that we have our formula for the measure up, I can modify this to incorporate our isBlank logic. And the logic is pretty straightforward. We simply want our formula to read, if the revenue measure is blank, return a blank. Otherwise, return the calculation that we see here, the calculation that gave us our revenue year-to-date measure to begin with. So before our calculate, I'll type if, and then the isBlank function, and then for the single argument to isBlank, I'll pass the expression that we're testing to see whether or not it's blank, which is our revenue measure. And then I'll close out that parenthesis. And then if that condition is true, if the revenue measure is indeed blank for a given set of coordinates in our pivot, we just want to return the value blank. And then if that condition isn't true, which is to say there is a value for our revenue measure for a given month in our pivot, we'll just return the measure we already had written to begin with. So now we'll add a final closing parenthesis at the very end to close out our if, and then click OK. And then we'll close out of our Manage Measures dialog box to see the results. And now if we scroll down to the bottom of our pivot table, drum roll please, we got exactly the result we were looking for. We see our year-to-date revenues all the way through the last month we have data for, but all those rows with no revenue and the same repeated values for year-to-date revenue are gone. Now, I don't want to convey the impression here that the isBlank function is only useful for this exact scenario. In fact, it's a very versatile function that you can use in all sorts of ways, but the general application is going to look something like this. Typically, you'll be using it to make sure that your measure returns blank if some other thing is blank or some condition is true, and otherwise just return the measure. Okay. After this little diversion into the isBlank function, up next we'll wade back into the realm of DAX time intelligence functions and explore a function that lets us compare different time frames side by side in a single pivot with ease. I'll see you then. Welcome back. Now it's time to dive into another of DAX's powerful time intelligence functions, date add. Whereas dates year to date and its cousins were great for viewing accumulated to-date totals for measures, date add's superpower is comparing measures and calculations across different time frames, month over month, year over year, etc. Like dates year to date, date add also manipulates the filter context within a calculate function. The difference is, instead of expanding the filter context to the beginning of a year, quarter, or month, it instead adds or subtracts a specified number of date intervals to the filter context of the current cell in the pivot table. So take, for example, the row in this pivot table for July 2019. The revenue for that month is $314,000. Our year-to-date revenue for that month is about $1.9 million. That number, which is the output of the measure we created in the last video, is the result of using our revenue measure as a starting point, but then extending its filter context backwards from July 31st, 2019, all the way back to the beginning of 2019. Now, by contrast, if you look at the value in the third column for July 2019 in this pivot table, under our revenue previous year column, we see a completely different number. But if you look back exactly 1 year in our revenue column to July 2018, you'll see a matching number. So this third column, which is being generated by a date add function, is the result of again taking that revenue measure and then changing its filter context in the pivot table. Except instead of extending the filter context backwards, we move it a specified number of intervals. In this case, we move it back 1 year. although the date add function is highly flexible, so we could move it backwards 6 months or forward 3 months. The bottom line is we're not extending the filter context, we're moving it, essentially offsetting it from the current position of that cell in the pivot table. So now that we know what date add can do, let's see how we can use it to build out a view like this. So to start, I'll set up a simple pivot table with year and month on rows and revenue on values. And now our goal will be to use the date add function to recreate that revenue previous year value we saw in the example pivot table. So to do that, we'll of course, as usual, create a new measure, and we'll assign it to our order details table and call it revenue previous year. And then to start, we'll, as usual, use our calculate function. And for the expression, we'll feed it our revenue measure. And now for the filter, instead of using a dates year to date or dates month to date function like in the last video, we'll use this date add function. Now, as was the case for dates year to date, and as is usually the case with time intelligence functions, the first argument is just going to be the dates column from our calendar table. So we'll enter that. Now the second argument is the number of intervals, the number of time intervals that we want to walk forward or backward in the filter context of our pivot table. Now that's really just a fancy way of saying if we want to compare the current month's revenue against the revenue from 6 months ago, 6 months in the past, on the same line of our pivot, we need to offset from the current location in the pivot table minus 6 months. So our number of intervals would be minus 6. Now in this case, we want to go 1 year back, so we could try minus 12 months, or we could do minus 1 years. Minus 1 years is a little more straightforward, so we'll opt for that. And now for the third argument, we'll enter the interval of time that we're offsetting forward or backward from the current location in the pivot table. So we're going back in time 1 year, and as a result, our interval will be just year. And as you can see, the word year is a special keyword that the date add function recognizes. Similarly, if you wanted to go back 6 months, you would just enter minus 6 for the second argument, and then the word month for the third argument. But what we've entered here should take care of what we're trying to accomplish, so I'll close out the parenthesis for our date add function, and then our calculate function, and then we'll format our measure as currency, check formula, and then click OK. And now let's add that measure to our pivot table. And just from a quick glance at the numbers, it looks like our measure works. Our August 2018 revenue number matches our August 2019 revenue previous year number. And it looks like our other numbers are lining up as well. Now, one cool application of being able to sit the output of a measure for two completely different time frames side by side in a pivot table is that we can create additional metrics that show how that measure changed from one time frame to the next. For example, a percent increase or a percent decrease. And if we wanted to do that here, it would be a relatively simple matter. We can go back to our measures and create a new measure, which we'll call year over year revenue delta. And then our formula will simply divide current revenue minus revenue from the previous year by revenue from the previous year. And then I'll add blank here as my alternate result argument, and then check my formula. And since this is going to be a percentage, I'll format the measure as a number, and then a percent, and then we can click OK. And now, just scrolling through the values of our pivot table, we see that these percentages make sense. In August 2019, our revenue was a little over $400,000, which is about a 54% increase over the previous August's revenue of $264,000. This ability to compare metrics over different time frames side by side is extremely valuable and also represents an incredibly common ask in the world of business intelligence. This sort of view would take a lot of work to set up without the power of DAX time intelligence functions. But as we just saw with DAX, it's really just a matter of setting up a couple of simple formulas. Now, one last housekeeping item before we go. As with our dates year-to-date function, our date add function is producing some rows in our pivot table, which, while technically valid, don't exactly make for a great user experience. So our data set only goes out through August of 2021. But obviously for September of 2021, there is such a thing as a previous year revenue value for that month, because we did have data for September of 2020. But of course this means that our year-over-year comparisons are going to always yield minus 100% because we're going from whatever revenue we had in the month in the previous year to zero. Now that's clearly a pretty confusing user experience, so what we need is to modify our revenue previous year measure to return a blank if our current month revenue is blank. So we'll go back into our measures, and then we'll edit our revenue previous year measure, and just like with dates year to date, we'll use the isBlank function. So we'll type if isBlank revenue blank, otherwise return the measure we've already created. Now let's check this formula to make sure it'll work, and then click OK, and then close out of this to see the results. And just like before, our little tweak with isBlank was enough to get rid of those rogue blank rows in our pivot table. Now, one thing I'd like to emphasize before we move on to our next time intelligence function is just how smart the date add function is. So say we were dealing with a leap year here, for example, and we were trying to compare one February to a previous February in which one of those Februaries had 29 days because it was in a leap year. Date add is smart enough to recognize that these months have different numbers and still compare the entire total for each month. Likewise, if we were comparing entire years to each other, and one of those years, being a leap year, had 366 days, date add would compare the entire total for both years. It's not going to get confused by the fact that the years have a slightly different number of days. The bottom line is that you can generally trust the date add function to be smart enough to correctly handle time periods with different numbers of days in them, and still make accurate period over period comparisons between these time frames. All right. Up next, we'll dig into yet another time intelligence function that makes something else that would have previously been thought impossible in a pivot table, rolling totals and moving averages, fairly straightforward. I'll see you then. Hey, welcome back. So before we move on to another category of DAX functions, there's one more time intelligence function I'd like to introduce you to: dates in period. So instead of year-to-date totals or month-over-month comparisons, dates in period gives us a way to introduce rolling totals, like, for example, the last 30 days or the last 6 months, and even moving averages to our pivots. Good luck accomplishing that in a conventional pivot table without DAX. So as you see here in our example file, we have a metric called revenue rolling 3-month total, which adds up for each given month of the pivot the revenue for the last 3 months. So if we look at the rolling 3-month total for the month of September in 2018, we see that number is around 600,000. And then if we add the totals for September, August, and July, going back 3 months in the revenue column, they add up to the exact same number. Even cooler to me is our 3-month moving average column, which instead of producing the total revenue of the last 3 months, instead gives us the average. So we see again for September of 2018, that 3-month moving average per our measure is $200,168, And then if we look at the average of July, August, and September, sure enough, that average is the exact same. Now, creating moving averages like this in a pivot table may sound daunting, but the dates and period function makes it surprisingly straightforward. So let's see how. Now to get us started, I'll create a simple pivot with year and month on rows and revenue on values. And now I'm going to use that dates and period function to create a measure showing a rolling 3-month total, which for any given month in our pivot will reflect the total of that month plus the prior 2 months for a rolling 3-month total. So it turns out that dates and period works a lot like dates year to date, which we used a couple videos ago. But instead of extending the filter context back to the beginning of some interval, for example, the current month or the current year, it instead extends filter context forward or backward by a custom amount that we specify. Now, while we can also customize the date we extend the filter context from, for most applications, you'll just want that to be the most recent or max date in the current pivot table filter context. Which is to say, if we're in a row of the pivot where the year is, for example, November 2018, the max date for that particular filter context is November 30th, 2018. Once we have that max date, the dates and period function expands the filter context forward or backward from that date, a specified number of a specified type of date interval, perhaps 2 months ago or 1 year ago or even 30 days ago. This is how we achieve rolling totals based on the date value of a particular address in our pivot. So now that we get the general concept behind the dates and period function, let's see what the syntax looks like. So I'll go to our Power Pivot tab and then create a new measure. And I'll call this one Revenue Rolling 3-Month Total. And then for our formula, as usual, I'll start with a calculate function. And then our expression will be revenue. And then for our filter, I'll now invoke that dates and period function. And as usual for time intelligence functions, our first argument will just be the dates column of our calendar table. And now the second argument is the date from which we are counting a certain number of intervals forward or backward. And again, typically this is going to be the maximum date, the most recent date in the current coordinates of the pivot table. So if we're in the cell of the pivot table for November of 2018, the max date that we would typically want to key off of is November 30th, 2018. And we can get that by just applying a max function to the date column from the calendar table. Now for our third argument, much like with the date add function, we just need to specify the number of intervals that we want to offset from this max date we're using as our starting point. And in this case, we're producing a rolling 3-month total, so that's 3 months in the past, so we'll use -3. And then for our interval, as you might have guessed, we'll just use month. And then we'll close out our parentheses and then format this as currency since it's just a filtered version of the revenue measure, and click OK. And now we'll add this to our pivot. Okay, so far so good. Spot checking these numbers, they look reasonable. So if I just pick a month at random, say April of 2019, we see our rolling 3-month total is 747,000. And then if I add up the numbers for February, March, and April, it looks like that's the total we get. Now taking this to the next level, where instead of a rolling 3-month total, we produce a 3-month moving average, is surprisingly easy. In fact, it's as easy as dividing our rolling 3-month total by 3. So let's create another measure called revenue 3-month moving average that simply divides this measure by 3. So I'll create a new measure and assign it to the order details table, and I'll call it revenue 3-month moving average. And then I'll use the divide function to divide our revenue rolling 3-month total by 3. And then I'll format as currency and click OK. And now spot checking a different month, let's say July of 2019, my 3-month rolling average is 302,694. So if I select May, June, and July, and then look at the auto-populated averages down in my status bar, we get 302,694. So it looks like our 3-month moving average measure is working as well. But there are a couple things we probably want to clean up before we'd want to present this file to an end user. For example, if we scroll back to the top, we see that our 3-month moving average measure is producing some deceptive and counterintuitive results for the first couple months of our data. That's because we're literally just taking the rolling 3-month total and dividing it by 3. So in the first month, where our rolling 3-month total consists of just a single month, we're basically just dividing 1 month's revenue by 3. So we end up with a number, $40,000, which, while it may be technically accurate, would also be confusing to a lot of end users and just doesn't add a lot of value in telling the story of our data. So really, the first number in our 3-month moving average column that really makes sense is this third one here, because that's the first number where we have data 2 months prior, for a total of 3 months to average. So what we need is a test to check whether there is revenue 2 months prior to the current cell in the pivot. Now that's quite a bit of logic to try to bake into this measure, so I'm going to create another measure called revenue 2 months prior, and then I can use the output of that to determine whether I want to return a blank or a value from our 3-month moving average measure. So back up to our measures button, I'll call our measure revenue 2 months prior. And now I'm going to use the date add function we saw in the last video to pull in the revenue measure 2 months prior to the current month in the pivot. So first the calculate function, and then the revenue measure will be the first argument, and then we'll use the date add function as our filter, with the dates column being the first argument of that function, and then we're going backwards 2 months, so -2 for number of intervals, and then month is of course the interval. So now we'll close out our parenthesis, check formula, format as currency, and click OK. And just as we'd expect, this revenue 2 months prior measure is returning blanks for those first 2 months of our data, because for those 2 months, there was no revenue 2 months prior. So now that we have this measure, we can use it as the basis of our logical test in our 3-month moving average measure. So we'll go back into that measure and edit it. So we'll select it, click Edit, and now we'll use our good friend is blank. So we'll say if is blank, and now we'll pass in our revenue 2 months prior measure. And then if that is blank, we'll return a blank. And then if not, we'll return our 3-month moving average measure. So now we'll check formula and click OK. And there we are. We got rid of those nonsensical values in our 3-month moving average measure. And at this point, we don't even need our revenue 2 months prior measure, so we can remove that from our pivot. And now just to make sure this report is ready for presentation, let's scroll to the bottom and see if we have any issues. And kind of similar to our last 2 time intelligence functions, our new measures are returning values for months where the underlying measure, that being revenue, doesn't even have data. And again, that's because in the case of our rolling 3 months revenue measure, it is valid to say that in September, even though we don't have data for that month, that there is such a thing as a rolling 3-month value, because we still have values to add for July and August. So what we need to do here, much as we did with our previous time intelligence functions, is add one more condition that says, if the revenue measure is blank, return a blank. So that will require us to edit our rolling 3-month measure. So we'll go back into our Manage Measures, and then select that measure and edit. And then we'll say if is blank revenue, return a blank, otherwise return the result of our measure. And then we'll add one more parenthesis for our if function, and then check formula, and then click OK. And now, as you can see, those 2 unnecessary rows in our pivot that showed rolling 3-month totals, even though we didn't even have revenue for those months, are gone. Okay, so up to this point, we've focused mainly on how we can solve various kinds of data problems with measures and DAX formulas, and that's totally okay. But we haven't given much attention to the how of writing DAX formulas. That is to say, best practices for writing these formulas in a readable, maintainable way that introduces the least amount of virtual clutter into our measures. So in the next video, we'll focus on one of the most foundational and useful optimization techniques in DAX, variables. I'll see you then. Hey, welcome back. So as you might have been noticing, our little list of measures really isn't so little anymore. Over time, we've managed to pile up quite the extensive collection. And while having lots of measures is fine, for the sake of streamlining our spreadsheets, we should really only create a measure if we think we would actually use it in a pivot table at some point. But it's quite commonly the case that we create intermediate measures that are used as part of a series of calculations to arrive at the result that we really want. Take, for example, our revenue 2 months prior measure. We're not really interested in that as something to display in our pivot on its own merits. We really just need it to test whether it's appropriate for our 3-month moving average measure to return a blank or not. Intermediate measures like this, then, are really just a means to an end. So what if we could somehow incorporate them directly into the measures we actually care about on their own merits, but without making our DAX formulas unreadable in the process? Well, it turns out that we can, by using variables in our DAX formulas. Now, variables are pretty much a standard feature in traditional programming languages, but may be a bit of an alien concept to you if you've only worked with Excel. In short, a variable in DAX is just the result of a calculation or even just a hard-coded value that we assign a name to. Then, once that name has been assigned to the value, we can reference the name, as opposed to the often complicated logic that produced the value to begin with, in subsequent layers of our DAX formula. This allows us to build multiple layers of logic on top of each other in our DAX formulas without making our formulas dense and unreadable. So as an example, let's see how we can factor out this revenue 2 months prior measure using variables. So the first step here will just be to grab the actual formula that generates that measure. So I'll go back into my list of measures, and then I'll select my revenue 2 months prior measure, click edit, and then I'll just copy that formula. And now I'll select my revenue 3-month moving average measure and edit that one. And what we're going to try to do here is replace this reference to our revenue 2 months prior measure with a variable. Once we've done that, we'll no longer need that measure, so we can delete it and make our Excel environment that much cleaner. So incorporating variables into your DAX formulas is basically a 2-step process. The first step is declaring the variable, which involves giving it a name, and then assigning a value to it, which in this case will be the expression, the calculation, that gives us our revenue 2 months prior measure. This will always come before the final result of the measure we're working on. So if you're using a variable in a DAX formula, you'll need to place those variables above whatever calculation is actually producing the result of this measure. So we'll click after the equal sign, but before our measure, and then enter down a couple times to create some space. And now, after the equal sign, we'll type the var keyword, indicating that we want to create a variable. And next is the name of the variable, which I'll call rev 2 months prior. Now note here that there are some restrictions on what you can name a variable, far more than I care to enumerate through or that you care to memorize. But the main thing to remember is just don't put spaces in between the words that make up the name of your variable. So now after we've declared the variable, we've given it a name, now we need to assign a value to it, and then we'll be able to reference whatever that value is by the name of the variable. So we'll say equals, and then just paste in that expression that we stole from our revenue 2 months prior measure. So at this point, we'll be able to reference the output of this calculation, which is the same logic that gave us our revenue 2 months prior measure, just by using this name that we gave our variable. So now, down in the meat of our measure, the actual expression that's generating the output of our measure, we'll copy that name of our variable and replace our reference to the revenue 2 months prior measure with the name of our variable. Now in theory this should work, but the little red squiggly line underlying our measure probably gives you a hint that it won't. But let's hit the check formula button anyway to see why. Well, unfortunately, this error message really isn't helping us out all that much. But the bottom line is, what has Excel so confused is that we neglected to include one additional keyword that absolutely must be a part of any measure that uses variables. And that is the return keyword. So if you use variables in a measure, after your last variable declaration, but before the logic that actually produces the result of the measure you're working on, you must include this return keyword. So after my variable, but before that final expression, I'll type return, and then hit check formula again, and now we have no errors. Now one thing I would like to point out that you may have already noticed before we actually lock this formula in is how much more leeway the DAX formula editor gives us for creatively employing white space, indentations, capitalization, etc. than with standard Excel formulas. So if you notice, I originally typed this if function in lowercase, but the rest of the function name's in uppercase. And instead of DAX automatically forcing me to type all the function names in uppercase, it allowed this. It also allows me to add as much white space as I want in between the various lines of my formula, and generally gives you a lot of control over how you want the code that you're writing to appear. In this sense, the environment in which you write DAX formulas is more akin to writing in a programming language like SQL or SAS than to writing conventional Excel formulas. But I digress. So now that it looks like our refactored measure should work, let's click OK and confirm. And it looks like nothing changed, which is exactly what we wanted. We weren't changing the logic of the measure in any way, we were just eliminating its dependency on this other intermediate measure. So the real test is going to be, what happens if we delete this revenue 2 months prior measure? So let's find out. We'll go back into Manage Measures, and then select that measure, and hit Delete. And the measure disappears from our pivot table, but our 3-month moving average measure, which had been dependent on it to work, still works. So it looks like our little refactoring operation was a success. Now, since refactoring and using variables is so much fun, I'm going to walk through one more example before we move on. So here we have a rolling 3-month total and a 3-month moving average. In my opinion, the moving average is the much more useful of the two measures. So what if we're really only interested in displaying that 3-month moving average in our pivot, and the rolling 3-month total was just an intermediate calculation that let us get to the 3-month moving average? Sounds like another opportunity for refactoring with a variable. So again, I'll go into my measures and grab that logic for the rolling 3-month total, and then I'll copy it and then go into my 3-month moving average. And now I'll add another variable, which again is something that DAX allows you to do. You can actually declare as many variables as you want in a single DAX formula, giving you tons of flexibility to create complex calculations that are still elegant and easily understandable. So we'll enter down another line and then type var, and I'll call this variable rolling 3-month revenue. And I'll just set that equal to the logic that we just copied out of that measure. And now I'll copy the name of our new variable. And now, down in the expression that generates the output of our measure here, I'll replace this reference to the rolling 3-month measure with the name of our new variable. And now that that's in place, we'll check formula and then click OK. And again, it looks like nothing changed, which is what we want. But again, the real test is going to be to delete that rolling 3-month total measure. So we'll go back into our measures, select that one, delete it, and there we have it. We've taken a metric that took us 3 measures to generate and pared that down to one single measure that is nonetheless easy to read and understand. That's the value that variables bring to your DAX formulas. Now, I also want to emphasize that this isn't the only scenario in which you would use variables. They're also helpful when you find yourself referencing the same expression or calculation multiple times in a single formula. With variables, you can simply name the result of that expression once, and then reference that name as much as you want in the rest of the formula. All right. Up next, we're going to switch gears a bit and begin our exploration of another category of functions in DAX, iterator functions. I'll see you then. Welcome back. So while we're on the topic of refactoring out unnecessary intermediate logic in our spreadsheets, let's consider our derived line total column here in the order details table. We really only created this column, which multiplies unit price by order quantity, so it could serve as the basis of our revenue measure, which sums the values in the line total column. But meanwhile, our line total column is just sitting there, taking up space in our data model. It would be nice if we could somehow incorporate the multiplication of unit price by order quantity inside our revenue measure. Then we wouldn't even need our line total column anymore. Let's first give this a shot by trying to refactor our revenue measure to sum the expression unit price times order quantity. So first I'll create a pivot table that we can use to test our revised measure. So I'll put region on rows, and then for our values, I'll sum unit price, order quantity, and line total. So now that we have the components of our revenue measure in place, I'll go into that measure and modify it, or at least try, by including our expression that calculates line total, that is to say, unit price times order quantity, right in the measure. So I'll select our revenue measure, click Edit, and now instead of summing line total, I'll instead sum the expression unit price times order quantity. Seems logical enough, although this red squiggly line under our formula should tell you that something's going to go wrong here. But let's click Check Formula just to make sure. And now Excel is telling us that the sum function only accepts a column reference as an argument. So basically, sum works when we try to sum the values in a single column. But what we're really trying to do here is to sum the output of an expression, that expression being unit price times order quantity. So obviously we're going to have to go about this in another way. So here's an idea. Since we know we're limited to summing only one column at a time, What if we sum unit price and then multiply that by the sum of order quantity? That way we're only passing in one column at a time to an individual sum function. So we'll put a closing parenthesis before our multiplication sign, and then we'll also sum our order quantity. And now we have something that looks syntactically correct, and we'll click check formula to confirm, and it looks like we have no errors. So let's click OK. And now we'll add our modified revenue measure to our pivot. Now in theory, our revenue measure should exactly match our sum of line total in the pivot table. But as you can see, the numbers that our modified revenue measure are producing are way bigger than the sums of the individual line totals in the pivot. So what's going on here? Well, the problem is our expression, which is the sum of order quantities multiplied by the sum of unit prices, doesn't operate row by row in the data. It instead simply multiplies the two sums together at every given address in the pivot table. So for example, in the East North Central region, if you multiply the sum of order quantity value, which is 58, times the sum of all the unit prices of items sold in that region, you get that total of $86,621, which is definitely not the actual sum of the line totals, which is just a little bit over 2,000. So basically, instead of our 58 total items purchased in the East North Central region being multiplied by their respective unit prices and then summed to yield our total revenue, we end up with a situation where all 58 are being multiplied by the sum total of all the unit prices for the 58 products, which is that $1,493 amount we see in the sum of unit price column. This obviously has the effect of vastly inflating our total, as we see in our revenue column. So what we need instead is a function that multiplies these individual values row by row, the unit price for a given order and the order quantity for that order, and then sums them, not the other way around. But we saw earlier that the sum function won't accept an expression, like the multiplication we're trying to do in this case, as its argument. The solution then is a sum function that does take an expression. And fortunately, DAX has us covered with the sumX function. Now, sumX is known as an iterator function for the exact reason that we just discussed. It evaluates an expression, like our multiplication expression here, for example, for every row in a table behind the scenes, and only then does it sum the results. So unlike sumX takes a table as its first argument that contains the set of rows that it will iterate over, and then our expression involving fields from that table is the second argument. So let's use sumX to refactor our revenue measure once more and hopefully get it to produce the right results this time. So let's go back into our list of measures, and then we'll select revenue and edit. And we can just go ahead and wipe out this entire formula that we had here before. And now for our function, we're going to type sumX. And as you can see, the first argument is a table, and that's the table that contains the fields that we'll be using in our expression. Now obviously we're multiplying order quantity and unit price from the order details table, so the order details table will be the first argument of our function. And then the second argument is the expression whose results for each given row we're trying to sum. And that's just that unit price times order quantity formula. So let's type that out. And then we'll close our parenthesis. Make sure we're formatted as currency. We'll check formula. That looks good. And then click OK. And look at that. Our revenue measure now exactly matches the raw sum of the line total field in our pivot. And the best part is, now that we have removed our dependency on that line total field, we can actually go ahead and just delete it from the data model altogether. So let's go back to our data model. and then select that column and delete. And then let's go back to our pivot. And it looks like our revenue measure is still working just fine. Now, one thing I want to emphasize before we move on is that SUMX is really just one of a whole family of iterator functions. There are also averageX, minX, and maxX functions, just to name a few. But these all work pretty much the same way. In every case, you're applying an aggregation to some kind of expression that is evaluated row by row for the rows in a table. Okay, now that we've seen the X functions in action, it's time for the sequel. So up next, we'll tackle the rankX function, which has some pretty incredible superpowers when it comes to ranking the data in your pivot tables. I'll see you then. Welcome back. So in addition to creating measures that produce aggregate values to display in our pivot tables, sometimes it's also useful to be able to rank those values and display the ranking alongside the value. For example, let's say we want a breakout of profit by product name, but would also like to see each respective product's profit ranked relative to the others. And as you can see, that's basically the view we have here. We have the overall profit for each product, but then next to that profit is where that product's profit ranks relative to all the other products. And going all the way down to row 19, we see that our shortboard has $1.6 million in sales, meaning that it's ranked number 1. Now, this kind of view is yet another thing that would have been next to impossible in a traditional pivot table, but can nonetheless be achieved with a single DAX formula. Let's see how. So our first step towards replicating that view will be to create a simple pivot table with product on rows and profit on values. So I'll create that. And now that we have our pivot table set up, we'll add a new measure that I'll call product rank by profit. And our goal again is to display alongside each product where its profit ranks relative to all the other products. So we'll go to our Power Pivot tab once more, Measures, New Measure, and again we'll call it Product Rank by Profit. And then for our formula, we're going to use a DAX function specifically designed for these kinds of problems called rankX. So I'll start by typing that out. And as you can see, much like SUMX and the other X functions, the first argument is a table. And while technically you can just use a plain old table in this first argument, the vast majority of the time, you're actually going to want in this very first argument to use the all function, and then feed that all function whatever column it is that has the values we're trying to rank. So I know that might sound a little bit weird, but let me explain why. So rankX ranks within the current filter context of the pivot table, which is to say for any given row in our pivot, rankX does its ranking based on the filter context for that particular set of coordinates. So that means if we don't modify the filter context that our rankX function is looking at, for the first row of our pivot table, for example, the row for balls aboard, we'll be ranking it against just the filter context for that particular row, which is balls aboard. So balls aboard, of course, will always be ranked number 1 of all the products that are balls aboards. So the solution then is to use the all function to wipe out that filter context. So now our rankX function is free to rank balsa board among all the different products listed. The general format here is going to be, if you want to rank something with rankX, you want that thing to be in your pivot table. You want that field that contains the values you're trying to rank in your pivot, but then in the table argument of your rankX function, you want to take that very same field and feed it to the all function. So now each individual set of coordinates in your pivot is free to rank the value at that set of coordinates against all the other values, because now you've removed the filter that field would otherwise apply to each cell of the pivot. In short, you're using all to override the filter context in the pivot table so that the rankx function is free to rank each of our products among the entire group of products and not just the product itself. So now that we understand why we would use all, we'll type out all. And then again, we want to feed the all function the same column that we're trying to rank. So that would be the name column from the products table. And now the second argument is basically the basis of your ranking. It's the calculation or measure that you want to rank these products by. So in our case, we're ranking them by profit, so the profit measure will be our second argument. And these two arguments, the table and the expression, are the only two mandatory arguments that rankx takes, and most of the time they're all you'll need. So for now, we'll close our parenthesis, and then because this measure is going to return a number that represents the rank, we'll format it as a number, and then a whole number. And we don't expect these numbers to get terribly large, so we won't use a 1000 separator. And now we'll click OK. And then we'll drag our new measure into our pivot. And there we have it. We have replicated the view we saw at the beginning of the video. Shortboard is still ranked number 1, and just scanning the profit by product, it looks like it is far and away our most profitable product. So this is already a very useful view, but you might be wondering how this rankx function is going to work if we add more layers to our pivot table. So let's say, for example, we want to add product category to our pivot above product name. Well, let's drag that in and see what happens. Very cool. So now our ranking is working within each product category. So instead of the products being ranked 1 through however many products there are, they're instead being ranked 1 through however many products are in a particular category. And then the ranking starts over again in the second category, and so on. So within just the category of beach supplies, beach chair is ranked number 1. Within just the category of riding supplies, skateboard is number 1, and so on. Now this is happening because while the all function we used as the first argument of our rankx function overrode the filter context coming from our product name column, it still isn't overriding the filter context coming from our product category column. So as far as our rankx function is concerned, the only filter context coming from the pivot is that product category. And that's why its current behavior is to rank all of these products within each product category. Now you might be wondering, what if you still wanted to keep that 1 through however many products we have ranking across all of the different product categories instead of within the product categories? Which is to say that if we see a number 1, we know that's our number 1 product overall, not just our number 1 product within a certain category. Well, to accomplish that, all you would have to do is add the product category field as a second argument to our all function. So just to prove that to you, let's go back into the measure and then select our product rank measure. And in our all function, we'll add product category. And then check formula and click OK. And now if we scroll down, we have the same ranking paradigm that we had before I even added product category to the pivot. So now when you see the rank of a product here, you know that it's the overall rank irrespective of product category. Now sometimes you might want this, but from my experience, the most useful type of view in a pivot table with multiple layers would involve ranking within each of those categories and not across all the categories. So I'll actually go back into our measure and change it back to the way we had it before. So we'll just remove product category as the second argument to all. And now we're back to this nice view we had before. Now it's also worth noting, just for clarity, how the rankx function determines what values get a higher rank versus what values get a lower rank. By default, larger values are ranked higher, just as you see here. Our most profitable product in each category gets ranked number 1, the second most profitable gets ranked number 2, and so on. Now you can customize this behavior in one of the optional arguments of rank X, but the vast majority of the time you'll want to rank larger values higher, which is why that's the default. Alright, up next we'll take a look at one more DAX function that puts a different spin on the whole ranking thing. I'll see you then. Hey, welcome back. So in addition to rank X, there's another DAX function that can apply ranking logic to your Power Pivot tables, albeit in a slightly different way. The top N function. So top N works kind of like rank X, but instead of ranking items displayed in the pivot table, it clips off the top N, where N could be 5 or 10 or whatever number you choose, records from a table based on a ranking, and then returns this subset of records. The ranking piece that determines which records qualify as top N works just like with rank X, but instead of the return values being displayed in the pivot table, they are typically aggregated as part of a measure. A classic example of top N's use might be to compare all profits, say for a given region, versus profits of the top N products, say the top 5 products as we see in our example here. This kind of view can help identify how top-heavy our business is, so to speak. That is to say, how skewed our profits are towards our very best-selling products. So without further ado, let's look at how we can put this kind of view together in Excel. So first up, I'll create our pivot table with region on rows and profit on values. And now that we have our starter pivot table in place, I'll create a profit from top 5 products measure. Now just to start, this is not going to show the percentage of our profits coming from the top 5 products. We're just going to show, alongside our profit measure in the pivot table, the profit that we're getting just for our top 5 products. So I'll hit our Power Pivot tab and the Measures button so we can create that new measure. And again, I'll call it Profit from Top 5 Products. So now for our formula, we're actually going to start with a calculate formula, unlike with rank X where we didn't need calculate and we just used the rank X function. That's because top N works by extracting the top N records from a table, which then serves as a filter on whatever measure we pass into the calculate function. So if our goal here is to filter our profit measure by just our top 5 products, we'll do a calculate on profit, and then our top N function will serve as the filter. So let's go ahead and type that out. So we'll start with our calculate function, and then our measure will just be profit. And then our filter will be our top N function. Now the first argument of this function is pretty straightforward. It's just, what do we want N to be? Do we want top 5, top 10, or what have you? So we'll choose 5. And now the second argument, which calls for a table, should basically be whatever table contains the field we're trying to pull the top N of. So if we're trying to filter for the top 5 products, then we should specify the products table, because that's the table that contains the product name field. So we'll go ahead and enter that. And now our last argument for top N works just like the second argument for the rank X function we covered in the last video. Basically, it's a measure or expression that determines which products are in fact ranked higher or lower. And in our case, that's profit, since we're ranking our products by profit. So we'll enter that. And then we'll close our parenthesis for the top N function, and then again for the calculate function. And then let's check our formula to make sure we didn't miss anything. And it looks good. So now we'll format our measure as currency, and then click OK. And now we'll drag our new measure into our pivot. And as you would expect, in every case the numbers are lower than our overall profit numbers, but in some cases they're quite close, because each of these numbers represents for the given region of that row in the pivot table, the profit from the top 5 products, the 5 products with the highest profit for that particular region. So just using our first region as an example, the East North Central region, we see that the profit from just our top 5 products was almost as much as our overall profit. So in that region in particular, our sales are pretty top heavy. And it's actually this kind of insight that the top end function is most effective at providing. And a more direct way of providing that insight is to, instead of showing a raw sum, a raw total of the profit from the top 5 products, to instead show the percentage of our overall profit that's coming from the top 5 products. Now, back in the Stone Age, several videos ago, we'd probably create a brand new measure that uses this measure as the basis for that calculation. But now that we know about variables, we don't have to create intermediate measures anymore. Instead, I can actually modify this measure to do exactly that without creating a new one. So to do that, I'll go back into my measures, and then I'll edit my profit from top 5 products, and I'll rename it percent profit from top 5 products. And since my overall goal is just to divide this number by the overall profit, I'll first declare a variable, which will just be the output of the formula that's currently generating this measure, and I'll just call it top 5 profit. And since we're using a variable, you know we have to use the return keyword. And now our expression is simply going to divide this top 5 profit by the overall profit. So we'll use the divide function, and then we'll reference our top 5 profit variable, and then our denominator will just be the profit measure, and then of course we'll include blank as our alternate result, and then we'll check our formula. Looks good so far. And now, because we're returning a percentage and not a dollar amount, we'll format our measure as a number and then a percent. And now I think we're ready to click OK. And there we are. Instead of just a raw number that forces us to compare the two numbers in our head to arrive at an approximate percentage of our profit coming from those top 5 products, we get what we really care about, which is just the percentage. And we were able to accomplish this cleanly and elegantly without resorting to an intermediate measure using variables. Now, one thing I want to point out before we move on, it typically doesn't make sense when using the top end function to include the field that you're taking the top end from in your pivot table. Now, this is one of those cases where the proverbial picture is worth 1,000 words, so instead of explaining it, I'm just going to remove region from our pivot and then swap in products. So the problem here is, because we have product on rows in our pivot table, that is now applying a filter to our measure. So even though our measure is trying to grab the top 5 products based on profit, and then sum those profits so it can ultimately find the percentage of our overall profit measure, because the pivot table is now passing a product filter in, we're really just taking the top 5 products where the product is that individual product in a given row of our pivot table. So for the very first row, our top end function is taking the top 5 products based on profit where the product is balsa board. And obviously that's just going to be one product. So the bottom line is, whatever it is that you're taking a top end of, you probably don't want that field to be in the same pivot table as your measure. Now this is kind of a low note to end the video on, so let's restore our pivot table back to its previous pristine state. So I'll remove product and then swap regions back in. Much better. Okay, so up to this point in the course, we've learned a lot about producing meaningful metrics from our data, but very little about how to present those metrics in a visually appealing way. But in the real world, the ability to create effective visualizations from our data is key to making sure the insights we generate are well understood by our audience. So in the next section, we're going to explore a series of techniques for adding visualizations to our Power Pivot tables to help us better communicate the story our data is trying to tell. I'll see you then.